Let's start by writing out the routing matrix here. Okay, the routing matrix for this problem is clearly the following. Okay, it is a 4x3 matrix because there are 4 links and 3 sessions. So the first column, okay, either write column-wise or row-wise, the first column corresponds to session A, which uses links 1, 3, and 4. So it's 1, 0, 1, 1. Okay, because the first, third, and fourth links are used, the second link is not used by session A. The second column corresponds to session B, which uses links 1, 2. So the first 2 positions are 1s and then 0. Third column, session C, which only uses link 4, so 0, 0, 0, 1. Okay, we can also see that link 1, the first row of the routing matrix, is used by 2 sessions A and B. So now we can write down the constraint, which is 1, 0, 1, 1, 1, 1, 0, 0, 0, 0, 0, 1, multiplying the rates of these 3 sessions. Since we label them by ABC, we call them XA, XA, XB, XC, less than or equal to the vector 4x1 vector, the link capacities. As mentioned before, we assume unit capacity on each link, 1 megabit per second. Okay, that's the constraint. And of course, we need all the XA, XB, XCs to be non-negative, to be physically meaningful. Now, the objective function is to maximize the sum of utilities. Let's say they all have the same utility shape and they are logarithmic functions to enforce proportional fairness. So maximize log of XA plus log of XB plus log of XC. Okay. Now this is an optimization problem. Maybe the 4th one or 5th one we've encountered throughout this course. And we have a couple of more coming up in future lectures. Okay, maximize a decomposed logarithmic, that's concave function, subject to linear capacity constraints and non-negativity. Now this matrix induces coupling, but as in the math material, we can decouple that. And we're going to run the following algorithm. Okay, the algorithm says that xi equals u prime inverse of the QIs, and PL equals current PL plus a step size times YL minus CL. This whole thing must be non-negative. Okay. Again, remember shorthand notation, QI is the sum of all those link prices along the links used by source I, and we'll also later use, this is used here, right here, the shorthand notation PL is the summation of the link, is the summation of the source rays coming from the sources I using link L. Okay, so with these shorthand notation, I'm just summarizing what we just derived in last module. All right, so let's write this out. Let's say we initialize the P's. That's P1 equal P2 equal P3 equals P4 at initialization times 0, or to be, say, 1 unit. The step size beta be 1 unit. In a homework problem, you will experiment with different step sizes, and you will see that when step size is too big, it will lead to it will lead to divergence. But when the step size is too small, then it guarantees convergence, but the convergence is very slow. So there's a trade-off between guarantee of convergence versus the speed of convergence, if you actually can get it. All right, but now we pick beta to be 1 to illustrate the algorithm. Okay. Now the iteration starts like this. Okay, at time equal to 1, we have the following. Okay, first look at the Q's. Okay, for session A, it equals P1 plus P2 plus P3 say from the last iteration. So that is 1 plus 1 plus 1 equals 3 units. And QB, the path price for session B, is 2. QC, path price for session C, is 1 unit. Well, this is easy to see. And then you say, well, it's just telling us basically that session A uses 3 links, session B uses 2, session C uses 1. Isn't this the flawed intuition we mentioned early on, right? Shouldn't we be counting the bottleneck links, not just the number of links? Well, we'll come to that actually right around the corner in the second iteration. But at this point, we have not captured that fact yet. As soon as the source starts responding, we will see. Now, the source rates, therefore, work like this. Okay, it is U prime inverse of Q, right? Well, for log utility function, the demand function, U prime inverse, is just reciprocal, 1 over Q A. That means 1 over 3, okay, and XB is 1 over 2, XC is just 1. These are measured in megabit per second. Okay. So at this point, you see that what happens to the link loads. You see that clearly the link load on link 4 actually exceeds what it has. Okay, we're adding 1/3 and 1. That's bigger than 1 unit that it has. The other 3 links are actually okay. So you expect at the next iteration, okay, the prices on the first 3 links should be less than, should become smaller, and the price on the next, on the 4th link should be higher. And that's indeed the case. Okay, now P1 should be the original P1 from last iteration plus beta, which is just 1, times the link load, current link load minus C. Okay, so last time it was 1, and now what we have is Y1, which is 1 over 3 plus 1 over 2, okay, minus C1, which is 1. Okay, this is already a positive number, so that's okay. This is in 3 decimal places, accuracy is 0.833. P2 follows the same pattern, so we have to look at basically 1 plus, well, half minus 1. That is 0.5. Similarly, you can write down P3, which is 0.333, and P4, which is 1 plus the load, which is 1.33 minus capacity 1. Again, this is the capacity, 1 megabit per second. This was the last iteration's price. Even though they both are 1, they have totally different physical meaning and units. Okay, and now with this beta, however, the units basically get converged. The beta numerical value is 1. Okay, so this means it's 1.33. Just as we expect intuitively, now the first 3 links prices drop because you're not fully utilizing the capacity, but the 4th link's price actually increases from 1 in the last iteration. And now we can write down the Q's. The QA is now this number plus this number plus this number, add up to 2.5. QB is 1.33. QC is 1.33. This implies next time the source rate XA is 1 over 2.4, which is 2.5, which is 0.4. XB is 1 over 1.33, which is 0.75, and XC is 1 over 1.33, which is 0.75. And now you already see that sessions B and C are being treated the same way, as driven by basically the topology. They both use 1 bottleneck link at iteration 2. That fact is implicitly captured because by this time we see both at the same number. Okay? And both are bigger than 0.4 for this session A that uses 2 bottleneck links. And now from X you can update Y, from Y you can update P, from P you can update Q, back to update X. And this iteration continues. And this is the iteration that you see over about 14 iterations. This graph shows the source rates, this graph shows the link cost. So you've got three curves, XA, XB, XC here, and you can see them converging to what? To the optimal solutions being XA star is 1/3. XB star equals XC star equals 2/3. Exactly the intuitive answer we mentioned as the proportionally fair and efficient and of course feasible answer to the num problem. The corresponding link costs at convergence are P1 star equals P2 star equals P4 star, which is 1.5, whereas P2 star and equals P3 star, which is 0. As you can see, we actually get to 0 within 4 iterations. And just to have a sanity check, does this make sense? Indeed, you can see the routing matrix multiplying this answer of 1/3, 2/3, 2/3 equals 1 times 1 and then 2/3, 1/3, 1, which is indeed less than or equal to 1, 1, 1, 1, the capacity of 1 megabit per second for every link. So it is feasible, and you can check its efficiency and you can check its proportional fairness. But you can also check that, hey, links 1 and 4 are kind of different, right? Because they are completely used up their capacity. They form the bottleneck link. And we can detect bottleneck links, okay, because the corresponding prices are positive by the so-called complementary slackness property in the Lagrange duality theory of optimization problem, which we will briefly mention in the advanced material part. We can say that when the optimal prices are actually non-zero, strictly positive, then the corresponding links must be bottleneck links. Conversely, if the prices for some links are actually, if the links are not bottleneck links, for example, links 2 and 3, they are slack. You are not even fully utilizing the given capacities. Okay? They did not cause the reason for you to stop adding rates to the sources. Then the corresponding optimal prices must be 0. This is called the complementary slackness property. All right, so that was a numerical example. You may feel a little disconnect between the first 2 modules of the course and the last 2 modules, okay? Between the engineering artifact of TCP congestion control protocols on the one hand and the mathematical models of capacity allocation through num-distributed solution. And actually there is a tight coupling. About 10 years after the invention of TCP, Tahoe, applied mathematicians and engineers collectively figure out a good way to understand the engineering artifact of TCP protocols. In particular, they have reverse engineered TCP Reno as implicitly maximizing a specific utility function, arctangent, and packet loss used as the congestion price, the link price, or mathematically the Lagrange dual variables piece. Whereas for TCP Vegas is being reverse engineered to be implicitly maximizing for logarithmic utility with delay used as the link congestion price. In other words, if you give me an engineering protocol, I can give you in return the underlying optimization or gain problem implicitly being solved for by these protocols. Now this is a weird angle. It's like You give me the solution, I tell you the problem. You may say, if I've already got the solution, why do I care about the problem? Well, knowing the problem is a good way to do forward engineering, for you to be able to understand why sometimes it works, sometimes it doesn't, and how can I improve its working. And indeed, reverse engineering had led to several interesting implications. For example, one implication is that for TCP Reno, if you increase the buffer size of these routers, it does not help with equilibrium packet loss. Mathematically, that's trivial to see because in TCP Reno, the num-problem is maximizing arctangent utility, okay, subject to link capacity constraints. The buffer size does not even come into the problem definition. So if you are the solution to a problem not even defined by buffer size, the solution cannot possibly depend on buffer size. And packet loss is the solution to the dual problem. So packet loss cannot be dependent on the buffer size at equilibrium. Physically, what happens is that you can make the buffer bigger and bigger. It will just delay the onset of congestion. You will just have to wait a bit longer until all the sources pump so much that for any finite size buffer, it will overflow it. So you make congestion start later, but you do not avoid congestion at equilibrium. Another implication this time for Vegas is that because it's been reverse engineered and shown to be maximizing logarithmic utility, it actually achieves proportional fairness in the allocation. If it can converge, now back to that question, can it converge? Well, mathematically we say we need small enough step size beta, which is not always the case for Vegas. Okay. But you can change the gain parameter at the sources as inspired by this reverse engineering and carry out a forward engineering. That's actually what has led to the development and deployment of fast TCP, which has been commercialized in certain long distance, high delay bandwidth kind of products, high delay bandwidth product kind of networks. Okay, so that's an example of going from reverse engineering to forward engineering. You know, delay-based congestion like TCP control protocol is going to give you some good result like proportional fair, provided you can make it converge. And now you can work hard to make it converge. Now we're going to go through a little bit of reverse engineering in the advanced material part of the video, and then a little bit further in one of the homework problems, if you're interested in going through this long advanced material section. As you can tell, it is the longest advanced material section, I guess, across all the lectures in this course. Okay. Now, this spirit of reverse engineering is not new to us. We were trying to reverse engineer topological properties such as small world and scale free, and we saw the potential pitfalls of reverse engineering without predictive power. Now we are reverse engineering functionality, especially protocols such as congestion control. And we have seen that you've got to validate it with empirical evidence, and indeed it has been, and it has been used for forward engineering. Okay. So in summary, we have touched upon quite a few different corners today. We talked about the principles, 5 principles of distributed congestion control. It is a networked version of the economics principle of demand supply regulation. We have also looked at the mechanics of some of the popular congestion control protocols in TCP. Then we looked at the mathematics of capacity allocation, formulated as an optimization problem and solved distributively. But equally important are the messages in the big picture. One is that the feedback signals can be generated and then used for distributed coordination in a network. In this case, is the internet. So we can view the internet, TCP, as the largest man-made machine solving an optimization in the form of num. Just like we can view Google PageRank as the largest man-made machine of eigenvector computation, you can view TCP in the Internet as the largest man-made machine implicitly solving for network utility maximization. And that insight came from this reverse engineering angle that says you can view network protocols like those controlling the Internet, analyze it, and even design it as a control law. It's easy for me to say today, but back 15, 20 years ago, it was quite an innovative angle. With that, we're going to stop our discussion on TCP/IP foundation of the Internet and move on into P2P network in the next lecture.